Hello, everybody. Welcome to round two of our senior capstone presentations. We have 6 presenters today. It's going to be, I'm going to give them an extra minute compared to last Thursday because we only have 6. So 6 minutes plus 1 question. So I guess hold your questions until they're done the presentation. One thing I wanted to mention before I forget is that for the space physics and astronomy majors, we have our physics forum this Friday at 2 o'clock to 3:30. And what's the room, Brennan? 52B is there. So we'll discuss the space physics and astronomy programs and take some feedback. Okay, well, let's go ahead and get started. Our first speaker is Bailey Wolf. Come on up. Yeah. Bailey's going to be talking about Wolf-Rayet astrophysics and pulsations. You all right?
Yeah. All right. Hi, everybody. I'm a little stuffy today, so I'm sorry in advance if I sound a little weird. But today I'm going to be talking to you guys about my project labeled Wolf-Rayet Astrophysics and Pulsations, or WRAP for short, a machine learning approach to test observations. Before I start, I would like to thank Dr. Noel Richardson and Dr. Christina Reynolds for putting up with me for the last 2 years. I know it can kind of be a pain, but thank you. All right, so first of all, I have to talk about what Wolf-Rayet stars are. They are O-type stars. They're really hot on the surface. All of their hydrogen, almost all their hydrogen is burned out, leaving all of the heavy elements remaining. Because of that, they have strong helium and nitrogen lines, and they also have very strong stellar winds. And because of that, all these factors lead to high periodic variability. And the periodic variability is what I'm going to be trying to classify between all these stars. So I feel like I have to talk about the machine learning process because I don't have very many data science majors in here. So the machine learning process, there are 2 forms. There's supervised and unsupervised. I work with supervised machine learning because some of my data set has labels. So first of all, how it works is you split your data set into 2 sections, the training set and the test set. The training set will have labels on it, and the labels that I will be assigning them are periodic or aperiodic because I'm trying to determine the periodicity of these stars. And the machine learning process that I'm going to be using is HCTSA, or highly comparative time series analysis, and I'm going to be using it to extract features from the training set to use on the test set. Basically, I'm going to be getting a set of features from a list of like 7,000, and that's going to create an algorithm from my training set that has labels. And then I'm going to assign those to my test set and hopefully classify them into either periodic or aperiodic. Okay, now I need to talk about my data set. My data set is basically a set of all of the Wolf-Rayet stars in the galactic plane that have a V-band magnitude less than 16. We picked the V-band magnitude less than 16 to avoid the background noise in the Milky Way, because you're going to have a lot of noise in your light curves and your Fourier transforms, and you don't really want to mess with that. The data that I used was taken from TESS, or the Transiting Exoplanet Survey Satellite, shown on the right there. And then I got a pipeline from one of Dr. Noel's colleagues, and then I tinkered around with it a bit to try and get it to work for me. Basically, the pipeline will extract the time, flux, power, and frequency values for my Fourier transforms and light curves. And those are in sectors because TESS works with sectors, and then I had to join all of these sectors together into one large light curve and Fourier transform. And then I could actually start doing my data analysis. So the data processing, this is the part that took me the longest. To start, we were trying to phase the light curves. So first of all, we had to find the peak of the Fourier transform. So in the top left of both of these plots, you have the Fourier transform there. And then the red line showing there is the peak in these two stars. And then on that peak, I took the points around it and then I fit a Gaussian to it. That would be the plot underneath those ones with the green line. And then when I found the true peak, the quote-unquote true peak, which is the black line in those, then I performed a chi-squared analysis to determine if the true peak actually makes sense. Basically, I looked at the reduced chi-squared fit value for it, and I created a histogram of all of the 216 stars that I had. And if it was beneath the unimodal distribution, then I would use the true peak value. And if I didn't, then I would just use the red line value that was on the Fourier transform. And once I got that, then I could fold the light curve on the peak that I used, and then I binned the data. That would be the plot on the right over here for both of these. That would be the black points that I have. I binned it into 100 values for each one. And then I could classify it. I looked at all of them, all 49 of my training set, and I classified them just looking at it. So the top one, that is Wolf rate 14. I labeled that one as aperiodic because there's no periodic signs whatsoever in there. And then I labeled Wolf rate 1 here as a periodic star because it's got periodic tendencies shown. Next, I'll talk about HCTSA, or highly comparative time series analysis. Basically, there's a library of 7,042 operations that can be used to identify discriminating features in the time series data based on lower dimensional representations of the data. And when you do this matrix multiplication among the 7,042 values, you get a single number of them for each one that measures the structure in the time series. And here is the plot. This is a very scary plot, I know. Basically, it's a 44 by 7,042 matrix of all of my training set stars. And it's got the one value that I was talking about before. And the orange values are ones that related to periodic stars, and the blue values are the ones that are related to aperiodic stars. And basically, I looked to see like the extremes, the most extreme points, and those are the top features that I would use to work on my test set in the machine learning process to classify these stars. And my next steps in this project are to determine those top 22 features, to build my algorithm, and then use it and run it on the test set to classify them. And then I will be publishing in the monthly notices of the Royal Astronomical Society. And that's all I have today.
Thank you, Bailey. We have time for one quick question. Yes, Em.
So you were taking the frequency with like the highest point peak on the graph, and then you did a chi-squared to see if it was actually the correct frequency. How often did you find that it wasn't the correct frequency to use?
So I want to say out of the 216 stars I had, around 40 of them had chi-squared, reduced chi-squared values that were greater than the limit that I set. It was like 60 or something. And those were the ones that I used the red peak on the graph, shown back here, right there. Yeah. I hope that answered your question.
Okay, thank you very much. Okay, so we're going to move on to our next speaker, which is Corey Jones. You want to come up? Get your talk ready. So Corey's going to talk about modeling dusty shells surrounding Wolf-Rayet binaries.
Sorry, how can I pull up the, not sure where they're kept.
Let's go here. That. That one.
So you can hover over the PowerPoint button at the bottom toolbar, and it'll give all the different options for it. It's
There
on
you
the bar,
are,
right?
right there.
presentation buttons.
Okay, that should do it. Okay.
Hello. Okay. Hi, my name's Corey, and I'm going to be talking about the geometric modeling of dusty Wolf-Rayet stars. And this project was led by my research advisor, Dr. Richardson. He's out there somewhere. There he is. Okay. Nice. So Wolf-Rayet stars are very massive, very hot, and volatile stars that are nearing the ends of their lifetimes. In preparation of croaking, they've blown off all of their hydrogen, or most of their hydrogen, and they have now exposed their very hot, powerful stellar winds underneath that layer of hydrogen. So in their spectra, you can see that there's a lack of hydrogen lines, and this is what we can use to clock these stars. Now, what I'm interested in is when carbon-rich Wolf-Rayet stars are in binary pairs with other hot, massive stars. And when they form binary pairs, the two sources of powerful stellar winds will interact and collide every orbit during their close approach. So, okay, that's just not going to play again. So every time that they make a close approach, the winds collide, they slow down very rapidly, and as the stars move away in their orbits, the material from the winds cools and condenses into dust. So when this happens over many different orbital cycles, that ends up forming these shells of dust that expand outwards as more orbits are completed. So this is WR140, and it has about 18 dust shells, I think. And this research team decided to geometrically model those shells to see if they can find out parameters about the star's orbit, the dust origin, the wind speed, and all other sorts of parameters. So our research project involved 4 different Wolf-Rayet stars: WR48A, WR112, WR137, and WR125. These images were taken by the James Webb Space Telescope, and these images became the basis of what we use to model their dust shell shapes. So I don't have time to go super in depth to each of the 4 stars, but I can give you a little bit of an overview on what makes each one of them unique. So this is WR137, and thankfully this one had a lot of parameters from other studies that we could use as a basis for modeling the dust shells. That's not super visible here, is it? Anyway, WR137 has this really nice edge-on kind of orbital shape that we can use to see those shells of dust expand on either side of the binary system. Oh, and this modeling program was done by a guy named Ryan White, who I've been collaborating with and has carried me through this entire project. This is WR125. It's very similar to WR137 in the way that it's an edge-on orbit, but it has a lot less. The dust covers less of the 360 degrees that we could possibly see. So next we have WR112, which is a monster. It is a total dust factory. It's very bright, it's very luminous, and it has a ridiculous number of shells that were actually kind of hard to model because there's just so many. And this is WR48A, and the guy who developed this modeling program, which is called Xenomorph, he actually did a preliminary model on WR48A that I use as a basis for my model. Now, it's not perfect, but you can see that it is mildly inclined. It's somewhat between edge on and face on. And that's it for our 4 different WR binary systems.
Thank you very much, Corey. We have time for some questions. Anybody have any questions on Corey's talk? I have, maybe while we're thinking about it, I have a question, very naive question. What actually causes the hydrogen to be blown away by the star? Is there a simple way to think about why that happens?
I don't entirely know. I kind of just work on what happens after that hydrogen's already gone.
Is it because it's the lightest? Or?
I think Dr. Richardson would probably know.
With all my students giving talks on wolf rays, I thought you'd picked this up by now. No, what happens is that there's 2 ways in which they lose their hydrogen envelopes. The first of which is a very strong stellar wind, which should happen for some of these. But the other way is that if they have a companion star, when the stars are close, they start to fill their Roche limit and they send material onto the other stars. So oftentimes the companion in these is spun up from a stripping of the star that becomes a Wolf-Rayet star. So it's strong wind actually is because of all of those interactions in the past.
What he said. Any other questions? Nope.
Okay, our next speaker is M. Begler. So M is going to talk about searching for evidence of a third star
There it is.
in the CV-SIR binary. So take it away.
Hello, I'm M. Begler, and I have been searching for evidence of a third star in the CV-SIR binary system. Thank you to Dr. Knoll, as well as Emma and Andre Nicolas for all your help during this project. So if you remember from Thursday, we've already seen this depiction of a Wolf-Rayet star, and we've had plenty of talk about what one is so far, but this picture is actually a pretty good depiction of the CV-SIR system, because CV-SIR is a carbon-rich Wolf-Rayet star orbiting a O star in a pretty tight orbit, like their period's about a month. They are orbiting close enough such that telescopes can't look at it and distinctly see 2 different stars. They just see a single dot in the sky, but we know it's 2 different stars because the light curves, like the amount of light seen, just periodically goes down, which means they're eclipsing each other. This dot in the sky is 2 stars in a trench coat. As well as going around each other, both stars release strong stellar winds radially outwards. That's basically the radiation of the star pushing small particles away from the star. And when these particles hit each other, they will form a shock interface where the particles are rapidly slowing down, and because the Wolf-Rayet star has much stronger winds than the O star, then it kind of conically wraps around the O star. Another known thing about the CV-SIR system is that it's known to be dust producing, but dust production is not a well understood concept on the whole. We know why specific stars cause dust, but not all of the stars. So let's look to other stars that are well researched to try and motivate, why is CV-SIR making dust? Well, WR104 is pretty famous. It's a triple star system with a Wolf-Rayet and a B star, which is also a giant star. And they've got a long period. They're pretty far away from each other, which means that their stellar winds have plenty of time to accelerate and reach some terminal velocity before reaching a shock interface, making the rapid deceleration of particles a lot more dramatic. And we know that that shock interface is where dust is being formed in the WR104 system. On the other side, though, Gamma 2 Vel, it is composed of identical star types as CV Sur has, and it's got a longer period, which means the two stars are further apart. The thing is, Gamma 2 Vel is not dust producing. It's been figured out that the radiation pressure is causing basically the radiation pressure that's accelerating one star's winds is actually slowing down the other star's winds. So once they reach each other, it's a pretty weak collision. We expect CV Sur to also be experiencing this radiative braking, as it's called. But that makes us wonder, why is it forming dust anyway? Because these are weak collisions. So based off of that and a few other things about the system that has been observed, we pose the question, what if CV Sur is 3 stars in a trench coat? AKA, is the dust being formed in the shock interface between the 2 stars we know about and a third undiscovered giant star pretty nearby? Well, how do we find this out? I've a couple years worth of data from GHOST and Maroon X, and it's spectral data. I'm able to look at the spectral lines and say, based off of what this emission or absorption line is centered at, the star is going at this instantaneous velocity at this time. And we can find that out through red shifting and blue shifting, aka the Doppler shift equation. And so I have a lot of data points, a lot of velocities compiled based off of several spectral lines. And then we compile them to create a nice sinusoid graph. It's sinusoid because the stars are going in functionally a perfect circle, and that sinusoid does not have to be centered at 0. The velocity it's centered at is how fast the star is moving towards or away from us. And my goal with all of this velocity work is to see, has that system velocity changed over time? Because if it has, that means it's breaking conservation of momentum. The best way to wrap our heads around this is that there must be something large enough and close enough by, such as another star, to exert a gravitational pull on CV Sur, or the Wolf-Rayet and O stars, so that it is changing the orbital path and the dynamics of the system. This is where I've been slowed down. The publicly available Python programs that model these sorts of things are limited for what we want to do, so we've been experimenting and trying other programs to do this sort of modeling. We have some preliminary results for if there's been a change in velocity over time, but this is very large error bars. So these preliminary results are also based off of a single spectral line, so we hope that once we've gotten the program down better and we've modeled more of these lines, that will shrink the error bars and we'll be more confidently able to say if the velocity has or has not changed. Thank you very much.
Okay, thank you, Em. We got time for maybe one question. Oh, Corey?
So far, what is it looking like? Is it looking like that third star does exist, or do you not have enough to tell yet?
I'm hopeful, but there's not enough to tell yet because other scientists have used other metrics like polarimetry to try and identify the presence of another star, and they haven't been successful. So it would make sense if there was another star there, but confirming that has been difficult in the past. So we're trying a new method for that.
Okay, thank you very much. Thanks, Em. Okay, next up is Sawyer Starr.
Thank you.
He's going to be talking about detecting Lorentz symmetry breaking with a scalar field. I believe he works with some guy named Quentin Bailey. I don't know who that is.
Okay. All right. Hello, I am Sawyer, and like he said, I'll be talking about Lorentz symmetry breaking. Very important question, though. What even is Lorentz symmetry? We need to know that before we can even talk about breaking it. Lorentz symmetry is a very important property of special relativity, which we can sum up by saying physics has no preferred orientation or speed. So we can do an experiment and flip our lab by 90 degrees and we'll get the same physics, or we can go half the speed of light and see the same physics. And we care about this because general relativity, which describes all of gravity, and the standard model of particle physics, while they're both successful models, they don't mesh together. We ultimately want them to mesh together, though, which is why we care about Lorentz symmetry breaking. We expect that they are branches of some unified theory, and that Lorentz symmetry breaking could be a effect of that unified theory when we go down to special relativity. And then this also allows us to work with the frame of relativity, which we want because it still is a successful theory. So how do we see Lorentz symmetry breaking? There are two different types. I have been working with explicit, which is a fixed background field, which you can sort of think of as just a breeze, a constant breeze. So if we align, say, a boat with the breeze, it will move. And so our experiment will get different results. But if we're not, then we see physics as we expect it right now. And you can see that Lagrange density on the bottom, which we don't really care about. All you need to know is that K is just how we describe the amount of symmetry breaking, essentially. Now the actual effects that we see. So the top three equations, you don't really need to care about what they do, we just care about the form. So even without Lorentz symmetry breaking, the form of these three equations stays the exact same, which is nice. The only thing that changes is the total energy that we see within the field, which is that bottom bit. And we get these extra terms on the right and then the far left. And normally we get p squared c squared plus m squared c to the fourth. And then we can choose plus for particles and minus for antiparticles. So maybe if our momentum is small enough, we could pick positive, and then if we have a negative momentum, we might be able to flip to an antiparticle. And now how do we actually detect Lorentz symmetry breaking? We hope to use, or we're looking at a Unruh DeWitt detector, which essentially makes use of the Unruh effect, where if you accelerate a particle, it will see a temperature within the vacuum compared to if it is sitting still. And we can use that to induce transitions between energy levels of this particle and see how these modifications affect the transition probability, which is related to that equation on the bottom, which you don't really need to care about except for that extra factor out front, which is good because that is still a very similar, that is still the same form actually, minus the factors out front of the unmodified case. So we can expect that overall the form of the transition probability is about the same, just with some extra scaling from these Lorentz symmetry breaking modifications. And then I mentioned earlier the possibility that maybe we could flip from particles to antiparticles and vice versa if our momentum is small enough, but that actually doesn't occur, which is good because that means our current understanding of particles and antiparticles is still good. And that's all I have. Thank you.
Hey, thank you, Sawyer. We have plenty of time for questions. Anybody have any questions? You could ask about what was the symbol for H. Maybe somebody might recognize that. Can you go back?
Yeah. This one?
Yeah, so anybody in my quantum mechanics class? That's the Hamiltonian H. So how would you describe the other equations below that?
Yeah, so this, the two in the middle are basically how you can, or describing the energy of created particles and removing energy from particles based on the momentum that we assign them.
Any other questions?
Oh, I think
you have
I'm
a question.
having.
How do you pick that momentum?
That would be dependent on the process you're looking at. So like if we shoot a particle at another particle with some momentum, then we can, I don't know exactly how you would include that in there, but it would be related to that. Yeah. I think Dario has one.
How many different K terms can there be?
16. So it's this is a 4x4 matrix essentially. But it is symmetric, so it is not exactly 16.
Okay.
So yeah. All right. Thank you.
Yeah, thank you very much, Sawyer. So, moving right along here. Next up is Logan Finke. Come on up, tell us about signatures of non-classicality in gravitational waves through bipartite detections, not entirely unrelated.
Okay, I think this is correct. Hello, everyone. My name is Logan Finke, and I'm going to be presenting a talk on signatures of non-classicality in gravitational waves through bipartite detections. Before I get started, I'd like to give a quick thank you to Dr. Preston Jones, my research advisor, and Joseph Roboto for helping make this project possible and just helping me along the way with the research. Now, first up, before we get started, we got to talk about the standard model and gravity. Kind of like what Sawyer was talking about, we're looking at combining these two theories of physics to try and make a cumulative theory that combines the standard model, which describes matter in our universe, and gravity. Now, as you can see on screen, we have a whole bunch of different particles. We have our quarks, leptons, but what we want to focus on are these bosons. Now, bosons are integer spin particles, and it just so happens that the particles that carry forces throughout our universe are bosons. But the only force missing from the standard model is gravity. Gravity, we have not been able to find a particle that actually associates gravity with this standard model right here. Gravity is a little bit weird. It's the weakest force in our universe, and this theoretical particle called the graviton is theorized to be massless, so it's going to be really hard to detect. Still, that has not stopped physicists in recent days from looking for the graviton. For example, in 2013, Freeman Dyson performed a series of calculations to try and figure out if the graviton could be detected at a singular point. Now, one of these such calculations seen on screen was for the cross-section of a collision of a graviton with any singular particle. And as you can see, 8 times 10 to the negative 65th centimeters squared is so impossibly small. You would never see this collision actually happen. It's just practically impossible. Nevertheless, researchers still search for the graviton through these single point detections, trying to find if we can actually see the graviton just through any singular event. However, what I'm here to talk about today is using bipartite detections to find signatures of classicality within gravitational waves. Now, instead of looking for the actual graviton itself, we want to set up a bipartite detector system similar to the Hanbury, Brown, and Twist experiment that we see up here on screen, where we have two different detector systems that are separated some distance that is actually overlapping the graviton's state function collapse. And using this detector scheme, we can look for a few different signatures of non-classicality within the gravitational wave. We have the measurement-induced entanglement entropy, the gravity-induced entanglement, and finally, anti-bunching. The first I'm going to talk about here today is the measurement-induced entanglement entropy. This is a quantitative measurement of non-classicality from the detector's response to the gravitational wave. Our two detectors are both the same, and they are classical systems. However, we're going to look at the quantum mechanical effects that are hidden within the detector's response to the gravitational wave. Importantly, measuring this does not actually depend on detecting a singular graviton, but instead observing the collapse of the graviton state function. If we construct a semi-classical model, that being the classical detectors but the quantum mechanical response, we can develop a bipartite detector state and assume that they are going to be entangled by the measurement of two indistinguishable gravitons with energy h bar omega. Now, I'm going to skip through some of the messy math that leads to this calculation, but if we take the trace of the density operator at detector A from detector B, then multiply that by the natural log of the density operator, we can find our measurement-induced entanglement entropy. If you look at the equation on the bottom right here, you'll see that the measurement-induced entanglement entropy is actually only a factor of the mean number of gravitons that are impacting the detector. This is really important, as if we get enough gravitons to impact the detector, then we may actually be able to measure this measurement-induced entanglement entropy. As you can see in this figure here, for higher strain amplitudes of the gravitational wave, we would be pretty easily able to model the measurement-induced entanglement entropy as a function of this mean graviton number, and it just so turns out that this is actually along the lines of intensity correlations, which is another signature of non-classicality within gravitational waves. So that means that we're doing something right. Next up, we can talk about the gravity-induced entanglement. Now, if we focus on our system being purely classical, and we have a gravitational wave impact our detector system, if we can find any quantum mechanical effects, such as entanglement, within this experiment, then that could be a possible signature of non-classicality within the gravitational wave, which is really all we're looking for. In terms of LIGO, if we can observe the quantum entanglement of these particles within LIGO's apparatus due to a gravitational wave, we could possibly prove the above statement. And this would be a pretty good smoking gun for quantum gravity. The last signature that I would like to talk about today is anti-bunching. As you can see in this figure here, this one kind of talks about photons and the different distributions that they can have during detection. Most common is coherent light. This is what you typically see, just a random distribution of light when you have a bunch of light going onto a detector system. But photons can actually exhibit this thing called bunching. This is really common for bosons, where if you detect a bunch of bosons, they kind of seem to clump up. As you see here, there are these different patches of photons. That kind of shows that bosons kind of have this like inherent property to want to bunch up. And this is a semi-classical effect. It's mostly quantum mechanical, but there are ways that you can describe bunching with classical physics, so not exactly what we're looking for. However, this last one right here, photon anti-bunching, this has actually been discovered to actually happen in photons, and this is a purely quantum mechanical effect. If we were able to observe anti-bunching within like graviton detections, then that could be a pretty good smoking gun for quantum gravity. Being able to see this purely quantum mechanical effect with no classical interpretation with gravitational waves, that's almost a done deal for quantum gravity. So overall, these are all of the different ways that we are trying to look for quantization in gravity. Does anyone have any questions?
Thank you, Logan. So any questions for Logan?
Did you say what causes the bunching and anti-bunching?
This is just kind of an inherent effect when you're like observing different particles. There's actually a paper released somewhat recently comparing what happens when you release like a bunch of bosonic versus fermionic particles onto a bipartite detector scheme. And they found that there was a pretty good trend of bosonic particles showing up with this bunching scheme. Meanwhile, the fermionic particles had this anti-bunching scheme where they're equally separated. So it's kind of inherent to the particle type, but we do see that photons, even though they're bosons, have exhibited this anti-bunching effect.
Thank you.
Any other questions? Oh.
How would you be able to tell if gravitational waves like experience or exhibit properties of anti-bunching?
We can do this through, I don't know if you were here on Thursday, but Joe in his talk actually mentioned the second order correlation function. This is a kind of measure of how likely two events are to be correlated with each other. If we could just observe that the second order correlation function of any detection is less than 1, then that means that anti-bunching is going on.
Thank you.
Mm-hmm.
All right, thank you, everyone. Thank you, Logan. We got to move on, but thank you. Next up is Lucas Murphy, going to talk about developing a muon template to analyze Mitchell electrons in the CCM detector. Let's work with Dr. Smith.
Alrighty, can you hear me, everybody? Awesome. All right, yeah, so my name is Lucas Murphy. I'll be talking about developing a muon template to analyze Michel electrons in the CCM detector for the search for light-dark matter. I'd like to thank Dr. Smith as well as Austin Schneider at Texas A&M for their help. I also want to thank the Planetarium for putting this together. Thank you, Eric. All right, so I just want to go over an outline of my presentation. First things first, I want to talk about the background. So we're going to review dark matter, maybe see some sources of it. Let's talk about the CCM detector and cosmic ray muon decay. I'll then talk about my filtering process, about how I look at these cosmic muon waveforms, how I build the muon template. Then I'll say how I classify these as Michel electron positive waveforms. And then we're going to look at how we integrate those and find the Michel PE distribution. So first things first, let's talk about dark matter. So observations over the century have concluded that there's some unaccounted for matter that can't really be explained by the standard model. So we see this in gravitational lensing. We see this in the fringes of galaxies moving faster than expected. So we know that dark matter is gravitational, doesn't emit light, and it's weakly or non-interacting with normal matter. We think a possible source of this dark matter could be weakly interacting massive particles, or we call them WIMPs. And theoretically, they could be produced at Los Alamos by this 800 MeV proton beam. So the CCM experiment can see WIMPs in the range of what we call light dark matter. From 50 keV to 1 GeV, that's about the energy of a fraction of an electron to about the energy of a proton. So let's talk about the CCM experiment. So CCM stands for Coherent Captain Mills. It's a 10-ton liquid argon detector at Los Alamos with 200 photomultiplier tubes. What happens at CCM is we have a proton beam from Los Alamos hitting a tungsten target, and we produce a shower of particles. What also happens is cosmic ray muons, just from the atmosphere, they can interact with the argon atoms in CCM and produce scintillation light. What's good about muon decay is that muons will decay into what we call Michel electrons, which are just normal electrons from a muon decay, but they have a well-known energy distribution with a maximum of 52.8 MeV, and that's due to the conservation of energy. If we see these signatures in the CCM detector, we'll see that sharp cliff at 52.8. We'd be able to use that as a calibration to see what's this detector's photoelectron output compared to actual MEV, which is what we're looking for. So how can we actually get these Michel electron signatures? We have a whole lot of muons, but how can we actually get the Michels from these? So first what we do is we only look at vertical muons going straight down into the detector. We do that by using cosmic watch detectors, which are just little muon detectors. Whenever a muon passes through 2 stacked cosmic watches, it will trigger the detector to start recording. We only look at muons that are in that recorded time region. They're time shifted to 9,000, 10,000 nanoseconds in their frame. We also only look at muons with mid-energy peaks that are above 500 PE, that's photoelectrons, or less than 5,000. Then we have this small kept region. Just from those, we take a normalized median of all those waveforms and we get a template of what an average muon should look like. After that, we can use this template to look for deviations in the muon template, which would be a Michel pulse. What we do is we apply 10 sigma error bars to the raw waveform, and anywhere that they do not intersect the muon template, it's flagged as a peak. So peaks that then pass stricter filters are called stored secondaries, which is our Michel category. Now, how do we actually know these are Michels? What we can do is we can fit the lifetime distribution, which would just be the time separation between a Michel pulse and the initial muon, and we should get the muon lifetimes. And as you can see here, we are getting the calculated values matching very well with the expected values. So we do know these are Michels. Now that we have a good sample of Michels, we want to integrate these and find their PE distribution. First, what we want to do is we only want to look at Michels that are inside the fiducial volume. And so we reconstruct the coordinates of each event, and we only look at the ones in the center. Then we integrate this charge, and we sum it up in a histogram, the Michel PE distribution. Now, we expect this to align pretty well with the theoretical Michel energy distribution, which is known very well from just particle physics phenomenon. And we expect some inefficiency in our detector. So matching this with a smear function, we get the following values, where a smear percentage of around 26.7% inefficiency and a ratio from PE to MEV of around 76.1. So yeah, from all of my research, we've concluded a few things. First, we've successfully built a muon template using a normalized median. We identified a sample of Michel electrons in the CCM detector. We experimentally verified the muon lifetimes, showing that we do have a positive sample of Michels. We found the energy resolution of CCM with that smear function of around 26.7%. And we calculated the PE to MEV conversion, effectively calibrating our CCM detector at this energy range. And that's all for me. Does anyone have any questions?
All right, thank you, Lucas. Questions for Lucas? Oh, we got one.
What was the motivation behind picking 10 sigma for your Poisson classification?
Yeah, so really 10 sigma was chosen just based on a quality factor. Anything lower, we started to pick up noise as Michels, and anything higher, we started to actually take out good Michel events. And so this was arbitrarily chosen as a quality factor, and it does go through more cuts to make sure that these are Michels. Noise will always be a problem, as I'm sure you're aware of. Thank you, though.
Thank you.
Any other questions for Lucas? I'll ask one quick one, and that's just what you've done here looks like process of calibration. So then my question is, what do you then do with this to look for the dark matter? What's the smoking gun in the experiment?
Yeah, so this has given us kind of an energy sensitivity measurement of this range around the 76.1 PE per MEV range. So what we're looking for is across the whole CCM detector, is this energy range constant? Maybe like the low energy ranges, they'll have a ratio. Our high energy ratio doesn't match with that. And if so, does that provide a good way for us to quantify possible signatures of dark matter. We'll know exactly what energy they have, and we're looking for basically excesses that could be beyond the standard model in this detector.
Thank you. Thank you, Lucas. And let's thank all our speakers. Congratulate them. They will be graduating next Saturday, as far as I know. So I will be there, so I will see you there. But congratulations to you anyway, ahead of time. And thank you very much for speaking. Thank you for coming to listen to, for many of you, your peers. And thank the faculty for coming. And that concludes our second session on senior capstone presentations. So have a great day. Thank you, everyone, for coming.